As Phil said, we have a lot to talk about in 15 minutes to do it, so I'm going to try and show you some things. I know we're trying to eat broccoli here, but I hope I'm giving you a little bit of dessert that's bacon or something like that. So uncertainty in climate change is one of the hardest things to talk about because of its sort of nebulous nature, and so I'm trying to reduce things to the way I speak to these things at the university level to my undergraduates. And I know you guys know a lot more about this than my undergraduates do, but I hope it's useful in terms of trying to characterize some of these big issues. So first of all, I was asked to do three things in this talk. The overall issue is uncertainty in climate projections, and projections is a word which has been used by the climate community for a long time because they're not ready to say we're making a forecast. What's the difference between a forecast and a projection? The difference is that a forecast is verifiable. We can actually go out and measure whether or not our forecast is correct. Is that true for the climate system? And that's one of the issues that we have to worry about here. A prediction and a forecast are considered to be the same thing. If you talk about the economic community and how they make predictions, I would say that it's very similar to the way in which meteorologists make a daily forecast. They have to ask, what's the probability that we actually got it correct? Can we add that probabilistic information to the process? So with that being said, one of the big questions is what's the difference between weather and climate? And I'll start off by saying, first of all, it's not weather and climate as in general. You have to put this in a specific context, and I'll give that in a minute. The next issue is how do we estimate uncertainty bounds for future climate change? And this is where I think Phil did an excellent job of leading us up to the general issue of how well can we predict global temperatures. I'll discuss a little bit about regional temperatures as well, and how do we interpret where the uncertainties are coming from for these different parts of the prediction process. And then the last thing, which is probably the hardest thing, how do we communicate uncertainty about these different things to the general public? And being in the press, in the media, you're in a perfect place where you have to test things out and see what works. And I'll say just a few words about that. Much of what I'm doing here is talking about how do I communicate these issues of uncertainty, and so hopefully that's a start for you in terms of the way we move forward. First of all, does anybody recognize this storm? Oh, it's not Katrina. Oh. Sandy. So this is Sandy. There's a lot of information on this image here. First of all, you can see that the path started down here in the Caribbean, was going straight west. Then it did a little loop, came down here south, and then it re-intensified and then it started heading north across Cuba, through the Bahamas, eventually started going out to sea, and then it got predicted to make a left-hand turn. So that's a great indicator of some of the problems we have about making predictions about things which are fundamentally leading to very, very high impact events. Hurricanes is one such example. Because this is a conference or workshop on the oceans and the uncertainty to do with sea level rise, I thought I would choose this one. One, it's local, sort of. I don't know if DC actually got hit by Sandy, but in the Northeast, definitely we got the center of the storm. Where's my thing here? The center of the storm actually went straight over my university when it came into Pennsylvania. After crossing into New Jersey, it went due west and finally wound down and spun down over the middle of Pennsylvania. This is the storm and the extent of it. As you can see, it's very large scale, probably half the size of it's about, in terms of its width, it would probably fit over about half the width of the country. So it was a very large storm as a result. And so the question is, was this weather or was this climate change? And how do we try and address that question? Some of you may have written about this in some articles already. What do I do when I talk to my students in the meteorology department at Penn State? Well, this is the assignment I give them. I show them this particular image. They all know what it is, and then we say, what makes it a climate event? What makes it a weather event? And sometimes I divide the class. You guys do climate, you guys do weather. And then at the end, we compare notes on what it actually means. Obviously, a hurricane is a weather event. It lasts for a day or two. It's at one level, that's what we know. On the other hand, it's a climate event because of the characteristics of climate that are influencing the strength and intensity and the path of the storm as it traveled up the East Coast and finally went inland. And so one of our goals, I didn't write down the lists that I've gotten from the students. We could talk about that a little bit more. But the issue is to try and understand what aspects of climate change are truly influencing the destructiveness of a hurricane itself. That's 10 minutes left. No. Yes. So it took me 2.5 minutes to see you. That's not so good. So as a result, we have these different lists. And in terms of the intensity of the storm, we have the overall warming of the oceans. The oceans are the source of energy for the strength of the storm. Therefore, the increasing temperatures in the ocean are at one level caused by climate change. Therefore, the strength of the storm can be tied to climate change itself. So that's one way in which we can identify how climate is influencing some of these high-impact weather events. And we have to consider the overall risk from these types of events as it increases in the future. And that sort of is one other reason I brought this particular issue up, is that the goal is not to say what climate change is happening or climate change is present, but to actually what are the risks to society that we have to worry about as we move forward with these types of predictions that we're getting from the climate community itself. Finally, at the end, after you've finished, add it to your lists and then turn it in at the end of the class. If you want to do this assignment, I'd be happy to take your papers and grade them if that would be fun. Okay, so weather versus climate. How do we know the difference? And this is where I introduce another concept, which is the fundamental way we think about climate has changed since we were kids. And the standard definition is always that climate is the average of weather, or it's the expected weather that we would get rather than the actual weather event that would happen. There's a phrase that we use is that climate is what you expect, but weather is what gets you. And so we have to worry about those sorts of definitions and how we talk about weather and climate to the students. However, it's based on an averaging period that's long enough to smooth over these fluctuations that we call weather. They can be day-to-day variability. In this case, that's what we typically think of when we think of climate. On the other hand, we can talk about time periods. Instead of being 30 years, which is the standard climatology, we can use averaging time frames, which are monthly, seasonal, decadal, or even hundreds of years in terms of what's the long-term climate conditions that we would talk about. And as a result of that, because the day-to-day variability is what we call weather, if we use a monthly average or a seasonal average, then that time frame defines what weather is. And I'll get to that, why that's important in a minute. So anything that's changing on a time scale much shorter than the averaging period is what we would call weather. And therefore, on a 30-year average, the year-to-year variability in the seasons is something that we would consider to be a weather event with respect to the long-term climate. And if I need to clarify that further, please ask me. So the modern definition, I think, of climate is it's the probability distribution of the weather events. Am I losing people? I'm seeing a few people. So we can come back to this issue in a minute. So the probability distribution is the collection of individual weather events that are potentially happening. And so the idea is that we're no longer talking about just the mean state of the system. We're also talking about the overall statistics of the system, which includes the extreme values. Hurricane Sandy, of course, is one of these extreme events. And we want to know how likely is it going to be that we're going to have these serious extreme events. Are they going to be more frequent in the future? Are the intensities going to change in the future? And how are we going to handle that risk to our society and infrastructures? So here's an example. This is a map of the sea surface temperatures over the last 3 months. And what you see is a general picture here. It's warm in the tropics where it's red. It's cold at the poles in the higher latitudes in the oceans. And we can see the warmest temperatures are here north of Australia, south of Asia, in the Indian and the Pacific Ocean. And that's what the mean state looks like over the last 3 months. But if I look at the anomalies, the ones which are going to be changing the weather patterns, and that's what really comes to bear here, is we actually see that over the North Pacific for the past 3 months, we've actually had a very large warm temperature pool relative to its background state, which is actually influencing the weather patterns over North America. And this is one factor which has led to the change in the jet stream position over the last 3 months. And I'm sure you've talked about or heard about the polar vortex and the wobbliness of the polar vortex in the past 3 months. And this large temperature anomaly creates a high pressure system, and it causes, therefore, the winds to come out of the north over North America and bring down the cold winds over North America here on the East Coast. And that then becomes one of the things which is now a weather event. This, in the ocean, this seasonal temperature change is going to be considered a weather event. And that's one of the points that I wanted to make overall. Okay. So getting to the predictions of climate change in general, are the models predicting the past? Now I'm getting more directly into IPCC type results. And the answer is yes. Phil showed that this is true for certain regions. I'm going to focus here on land surface on the left, land and ocean surface temperatures in the middle, and then the ocean heat content changes here for the globe. And so this is one way where we look at the models and their ability to predict the temperatures of the past. And as Phil mentioned, the red swath here is where we're actually modeling how well, with all forcings included in the system, are we able to predict land surface temperatures, and ocean temperatures as a result. So we're doing pretty well in terms of how we're able to make these predictions. The uncertainty comes in where we have this red band which is surrounding the observations shown by the black line here. And that uncertainty information is telling us that we're only good, that uncertainty information is coming from the climate models themselves and the ability for the various climate models which are used in the IPCC report to reproduce those temperatures that we see there. If we go a little bit further, we can look at all of the regions of the globe and ask what's happening. The yellow ones here, or tan, are all land temperatures. If we move on, we can actually look at sea ice coverage in the Arctic and the Antarctic. And we can look at the ocean temperatures across all of the different regions of the ocean. And in general, the observations in black are within the pink band, which is our climate change detection and attribution result, saying that the observed climate over the past 100 years is a result of human-induced causes. So, with my 2 minutes left, 30 seconds left, what I wanted to try and get down to is an issue of where are these big uncertainties coming from? And so I thought we'd go back to basic physics. What's happening with it? How do we predict the flight of a soccer ball? It's the World Cup coming up, so I thought this would be appropriate. The first thing we would like to know is how hard are we kicking it? This is analogous to the climate forcing. We don't know it specifically, but we have to include that in the result. The next one is how far does it fly? This is the climate modeling aspect. What's the response of the climate system to the forcing that's being applied? And then finally, what are the things that we can't control? What are the random effects, like what's happening with the wind, what's happening with the rain, the mud, whatever else is going on in these cases? And this is then, in the climate world, this is internal variability, or it's external factors that we can't control. And so in terms of the what's happening in the climate world, we have uncertainty in the forcings, the scenarios for future emissions. We have uncertainty associated with multiple climate models. They have different resolutions, different components, different processes, therefore different representation of the internal physics. And then finally, we have this issue that we have uncertainty in the initial condition. We can go into that. The uncertainty in random factors like volcanoes going off and cooling the planet. And we can talk about that as well. And then finally, we can go even deeper into what are all of these different sources of uncertainty. Are we talking about long-lived greenhouse gases? Are we talking about aerosols, land use change? And on seasonal and decadal timescales, what's happening with the ocean and the sea ice and the volcanoes? And then the last issue is in terms of the climate response, how sensitive is the system to this set of forcings that we have up here? And that can be talked about in the sensitivity of temperature, precipitation, sea ice, sea level rise, so on and so forth. And now I'm really late. So this is an example of a figure out of the IPCC in Chapter 9 where we have over 30 different models, 25 different models or so showing up on the same figure, and it's just looking at the global mean temperature change over the past 150 years. What you see is that on an individual case, you wind up with lots of small year-to-year variability. And the average of all of these climate models is fairly closely matching the black line, which is the observations. And it's this particular issue of how much of the noise do we see here is due to internal variability, and how much is due to the forcings by the natural and the human forcings that we had over the past 100 years. And that's actually what goes into this formal statistical framework called detection and attribution. And that, in our chapter on climate model evaluation, we specifically asked, are the models good enough to do this? And Chapter 10 it formally looks at the climate change detection and attribution problem and is asking how well can we reproduce the historical trends. The climate change uncertainties, what do we know and what don't we know? In one sense, what are our limitations and what are our strengths? So limitations, we have only one record of Earth. We can only compare our climate models against one record of the planet over the past 100 years. Or we can go back deeper in time and look at paleoclimate situations and ask whether the models are capable of reproducing those. We have limited resources to understand the uncertainty associated with things like the internal variability. And then finally, the limitations are that the system is complex and that new risks emerge after you start looking at the deeper interactions between all of the different parts of the system. What do we know? Well, we understand the fundamental science of weather and climate. I think that's fairly solid. We understand how the past changes have occurred. And we know that if we know the risks, if we can quantify these uncertainties, we can use these pieces of information for planning purposes. And the last slide I have is on how do we communicate. And I'll let you read this and take questions right now.